Okay, so let me start with thanking the organizers for putting up this very nice meeting. I'll be talking about active glassy dynamics in systems of self-propelled particles. If you quench the temperature of a liquid from high temperature to below its melting point without allowing it to form crystallization, then the viscosity and the relaxation time of the system increases quite rapidly as you decrease the temperature, and this is known as glass. And working definition of glass is when the relaxation time becomes of the order of 100 to 1000 seconds. Note that there is no thermodynamic transition associated with the glass transition. If you take a snapshot of a liquid and a glass, they look nearly identical, but their dynamics are markedly different. For example, the 2-point correlation function in a high temperature liquid decays quite fast, exponentially fast. But as you approach the glass transition, a complex relaxation scenario appears, and the function first decays towards a plateau, and then from the plateau in long time, it goes towards zero. It also shows steep increase of viscosity and relaxation time and dynamical heterogeneity. That is, fast and slow moving regions coexist in the same system at the same time. Now, why do we care about glass? Because glasses are everywhere in different aspects of real life, in different scientific problem. Also, recently it has been shown that in many important biological processes, also the glass-like dynamics is seen. And today I'll focus on this aspect. In the year 2001, the group of Friedberg, they coated ferrimagnetic microbeads with some synthetic polypeptide, and they attached them with the integrin receptors on cell surface. So this system allowed them to measure via microbiology experiment the properties of the cytoskeleton. And they showed that the cell cytoplasm behaves as a glassy material existing close to a glass transition. A number of phenomenal experiments appeared ever since, both from the group of Friedberg and as well as by others. And by now, it is well established that the cellular cytoplasm behaves like a glassy material. Now, biology is organized at different layers at different length scale, and this is example from a different length scale, where it was shown that collective motion of cells for different biological processes also show glass-like behavior. Now, these examples are not some random example where you see glass-like behavior. They have profound biological importance. For example, the glassy dynamics of cytoplasm is fundamental for life, for cellular organization via transport to give the mechanical properties of the cell. Also, the glassiness in collective dynamics is crucial for many processes, for example, wound healing, cancer progression, embryogenesis, pattern formation, etc. Apart from their biological relevance, also there is another motivation of this problem, where exploring this glassiness in these systems extends the scope and the extent of the problem. So the hope here is to gain more insights on the different aspects of the equilibrium problem itself. Now, these systems are different from usual equilibrium system. Most of the glassy characteristics, they are although similar with the equilibrium glassy properties, there are important differences. And the difference comes because these systems are different, they are active. What it means that these systems consume some energy and do some work. And this work is quite different from the work that we know for equilibrium system. For example, the constituent of these systems, they can divide, die, differentiate, decide their own fate, propel themselves, change conformation, modulate interaction, can be confluent, etc., etc. So clearly, developing a comprehensive theoretical framework for this system is a daunting task. And the trick here is to take one aspect at a time, try to understand that on top of the well-known usual equilibrium properties. And from now on, I'll be talking about self-propulsion alone. So active system of self-propelled particles. These particles are associated with a director with them. They move along this director with a certain self-propulsion force F naught and a persistence time tau p. Now, even with self-propulsion alone, these systems are clearly driven out of equilibrium. And then the question becomes, then what? Can you still apply the usual well-known tool of statistical physics, or do we need something else? To understand how to answer this question, I will paraphrase Giorgio Parisi here from this paper in Nature in 2005. When we go out of equilibrium, new properties and behavior appear. If the departure from equilibrium is substantial, we must resort to different tools. But the situation is different for systems that are only slightly out of equilibrium. A separation of timescales appear, and so fluctuation dissipation ideas can still be applied. So now the question becomes, how far from equilibrium is active matter? And this is precisely the title of this paper by Mike Cates and others. And the answer turns out to be not too far when tau p is small but finite. So they showed that these systems can follow an effective fluctuation dissipation theorem akin to that of thermal equilibrium system. In fact, this question has been addressed in many contexts for many different systems in experiment, simulation, theory. And here I have shown some theoretical result from mode coupling theory, which is one of the most popular theory for glassy dynamics. Now let me give you just an overview of what is the essence of this theory. The idea is to first write down the general theory for a non-equilibrium system and then take the waiting time tending to infinity. So in that limit, the active system will go to a steady state, and essentially you get the non-equilibrium mode coupling theory for active glasses. Now in the derivation of this theory, we did not assume any fluctuation dissipation ideas, but the cost we must pay that the theory becomes in terms of both the correlation and the response function, and their ratio is known as the effective temperature, which is shown here. But you can do even further. You can develop a scaling analysis assuming an effective temperature scenario, and these are the results where these lines are the scaling analysis and the data are the numerical results of the non-equilibrium mode coupling theory, and they agree quite well. So now we can compare with simulation data, and these are characterizing the relaxation dynamics of a glassy system, active glassy system, and the work is done in collaboration with my colleague Saroj and his student Kollol, and more detail can be found here. So I just want to point out here, okay, so these lines are the theoretical prediction, but not all the lines are simply fit to the simulation data. So once you have the theory and one set of simulation data, you can simply fit that data with the theory, and all those free parameters are now fixed. So now you can compare and the prediction of the theory with the simulation data, and these are just that. So for example, this line here is not a fit. It's simply the theoretical prediction plotted along with the simulation data, and they seem to agree quite well. Okay, so to test how far one can use this effective temperature type of idea, we devised this following test. I will choose a set of parameters of different activity and temperature such that the effective temperature parameter remains the same. Now for this system, if this idea works, you will expect that the relaxation time for these different systems will be same. In fact, what one would expect that the 2-point correlation function will overlap with each other, and this is precisely what we find for two different systems in simulation. Now, when we plot the chi-4, which characterizes the dynamical heterogeneity, and the chi-4 peak is related to the dynamic heterogeneity length scale, in that case, we see that they are defined. So if T effective is just like the equilibrium temperature, you would expect a overlap of all these curves, but it doesn't happen. So that shows that effective temperature is actually quite different from the equilibrium temperature. And another question, can mode coupling theory, which is one of the popular theory of glass, can it capture this behavior? Now, mode coupling theory has a strange status. It is well known that the theory is precisely wrong, but this is the best we have. There are instances where the theory fails miserably, but also there are instances when the theory does surprisingly well. So it's a critical theory. There is a length scale and a time scale associated with it. They're both monotonically related, meaning given a length scale, you will get a time scale and vice versa. But in active system, this very relation breaks down. So with a given tau alpha, with a given relaxation time, you find different length scale for the system. So it, in one hand, shows that T effective is different from equilibrium temperature, but also the question, does mode coupling theory capture this behavior? So we wrote down this theory, mode coupling theory, for the 4-point correlation function, which characterizes the dynamical heterogeneity. And then one can numerically solve that. So for this system, we have taken in such a way that their effective temperature is same, and what we find that the 2-point correlation function overlaps with each other. So this one would expect. And also in agreement with the simulation, the chi-4, which is the 4-point correlation function, they are defined for this system. So mode coupling theory does capture this non-trivial aspect of active glass. So to conclude, fluctuation dissipation ideas can be applied to active systems when activity is not very strong. Although relaxation dynamics is equilibrium-like, activity non-trivially affects the dynamical heterogeneity aspect in active glasses. And this effective temperature has the essence of, which is quite different from equilibrium temperature. And the mode coupling theory does capture these non-trivial aspects of this effective temperature. Thanks.
Okay.
So can you theory explain the short time peak in chi-4? So in your simulations, that short time peak is there.
Yes, so the short-term peak, actually one needs to look at the beta regime and also with different k vector. That part we haven't done. So this theory that I was showing you is a schematic form, which is known as schematic form, where you suppress all the wave vector dependence. But with wave vector dependence, one can write down the theory, and that requires a numerical solution, which is a bit daunting. We haven't done it yet, but we are looking at it.
So basically, it's only limited to
I think it
the alpha
should
eclipse.
capture that aspect.
Huh?
I think it should capture that aspect as well, but we haven't done it yet.
Okay, thanks.
Yes, so I was wondering this by this active glass formulation, like can you define effective temperature for this cytoplasm that glassy?
Yes, so the effective temperature is basically the ratio of the correlation to the response function, and that you can always define. And it has been done not by us, but some other group. And in that system also, it seems that the effective temperature idea seems to work.
I see.
Correct me if I'm wrong, but I think your Chi4 peak increased with activity, is it?
Yes, yes.
But okay, but it also shifted a little bit to the left, or is that? Can you resolve that? The point in time, the x-axis.
So here the relaxation time seems to remain the same.
Is it? Okay. See, because I thought if you increase activity, there is work that says that, for instance, metabolism actually fluidizes the cytoplasm.
Yes, exactly. So, but
So-
here we are taking the parameters in such a way. So, sorry, I just showed the activity parameter, but also there is a temperature. So, temperature
okay.
I'm keeping the effective temperature same. There,
okay.
I would expect that the relaxation time remains the same.
Okay. Thanks.
This is for fixed persistence because in the simulation they kept the persistence time fixed.
So if you keep f constant and change persistence, what do you anticipate?
So there are actually two types of model. In one type of active model, you would expect that the system is driven away from the glassiness. In the other one, you expect that the system is driven towards the glassiness. And both of them can be captured within mode coupling theory. So I haven't shown the result, but
So in terms of Chi4 peak amplitude, what do you expect? They expect a re-entrant and all sorts of stuff that goes on.
so that for the Chi4, I haven't done that, but only with the 2-point function, it is consistent with the simulation data.